Here we go. So as a reminder, peer reviews are going to be due next Monday, and you only have to do one of them. So you've given 2 people to review, you only have to review one of them. So you can pick which one you want to review if you want. But I would recommend if somebody else has reviewed one of your people, then you review the other one, so that everybody has a review. Easy. People that did not do the essay don't get a peer review. So you have to post an essay for you to get a peer review. I've been going through and grading the essays. If you've gotten a 10 so far, that doesn't mean that you will get a 10 eventually. If you don't do the peer review, it'll drop to a 5. But so far so good. I've seen some minor mistakes. One was the Marxist theory of truth was that which is beneficial is that which helps the revelation. Which, the revolution. In other words, promotes the communist revolution. That's the Marxist theory of truth. And the other one was confusing legalism with deontology. So these are not the same concepts. That which is legal is that which is morally correct is not the same thing as Kantian ethics or deontology. Yeah. Okay. I did argue with one of these guys online over the weekend, and the guy didn't accept the reality of the massacre in Cadden Forest. It's one of the darkest episodes of history. So the Russians, after they invaded Poland in conjunction with the Nazis, which is something that a lot of people don't know about, Stalin and Hitler were secret pen pals, and they conspired to invade and divide up Poland between them, part of the Molotov-Ribbentrop Pact. And so Hitler invaded Poland. The Polish army was doing their best to hold off the Germans, and then Russia invaded from the other side. And at first the Poles were like, oh, they're helping us. No, they weren't helping. They were there to kill them. And so they massacred large numbers of Polish leaders and things like that in Cadden Forest. And so I was, and there's overwhelming evidence that the Russians did it. So Stalin at the time blamed the massacre on the Nazis, and so I was talking to a guy today or this last weekend, that believes Stalin and doesn't want to countenance any evidence to the contrary, despite it being overwhelming, despite the Soviet government itself admitting that it was a Stalin, excess. Okay. So, yeah, it's, that is that. I'm working my way through your essays right now. Okay, so let's talk more about algorithms. So if I wanted to find the smallest element in this array, what step-by-step process? So I've got 4 numbers here. That's what an array is. An array is just a bunch of numbers in this case. So if I wanted to find the smallest number, could you guys in chat come up with a step-by-step way? It don't even have to worry about what a array is or anything like that. Just imagine you got 4 playing cards, or I'm trying to see if I have any cards around here. I guess I don't. Or dominoes that have different numbers on them. if I handed you a bunch of dominoes and asked you to find which one had the biggest total number on it, what process would you go through? Go ahead and type that up on go ahead and type up step-by-step algorithm for that. Well, let's just say I handed you a bunch of dominoes. So this one has 7 dots, this one has 1 dot, 5 dots, 2 dots. So if I'm asking for you guys to find the smallest number out of these 4, your first step would be to sort it. Okay. And then you would pick off the smallest one. So this is it would work. It definitely work. It is, however, not very fast. So remember how we said sorting, especially if you're doing the most basic form of sorting. Sorting involves finding the minimal number over and over again. And so if you're trying to find the minimal number by sorting, and your sorting algorithm works by finding the minimal number, then you're kind of in an infinite loop at that point. Sorting something takes roughly this amount of time. So if you have a million dominoes and you're trying to find the smallest number in them, and the log base 2, for those of you that don't remember algebra, it's saying 2 to the, it's the opposite of exponentiation, let's put it that way. So the log base 2 of a million is about 20. Okay. So in order to find the smallest domino out of a million dominoes, you have to do 20 million steps, to do 20 million operations. Whereas I could find the smallest domino in a million steps. So that would be 20 million versus 1 million, right? So sorting it to find the smallest number would be 20 times slower. Who are so wise in the ways of science? Yeah, great Monty Python reference. Yep. So go rid of the ones with lots of dots. You do that, right? Just kind of toss out the big numbers. I don't know. Now the way that Ramsey's put it would be the right way of doing it. So what to find the smallest domino, you would set the first domino aside. So in this case, the 7. Take that, put it aside, and then you're going to loop through the dominoes. In other words, you're going to go through all the different dominoes. If any of them is smaller than the one we set aside, replace the domino set aside with it. Formatting's a little weird there. But basically, what that means, like, so you start off by setting the first domino aside. So we're going to have the 4, 1, 2, 3, 4, 3 up there. And then we're going to loop through all of the different dominoes. And so we come to this one here that has 1. So that is smaller than the one we have set it aside. So we discard the old one we have set it aside and set aside the 1 instead. Then we get to the 5. Is the 5 smaller than that? Nope. Is the 2 smaller than that? Nope. And we're done. So this one is the smallest domino. Okay. So if you had 1,000,000 dominoes, you would be able to find the smallest domino in 1,000,000 steps. You'd go through one domino at a time and see if that one's the smallest. If it's the smallest, then you get rid of the old one that you set aside and you set it aside. You just keep going through the whole thing. And so sorting it is unnecessary. You actually don't need to know the exact ordering of all these different dominoes. All you need to know is the smallest one. So, all right. All right. So how would you guys go about finding the maximum domino? The domino with the most dots on it. What approach would you guys take for that one? Find the one with none higher than it? Yeah, I mean, that's kind of what we're asking to do. Big domino finder.exe. Yep. Yeah, you guys are on the right track, I think. Yeah. Huh. And so, same algorithm, except change the smallest with the biggest. There you go. Okay. So, what about if we had a map of the United States? What the heck? Maybe a real map of the United States. There we go. Okay. So let's say we've got a map of the United States. Okay. And you wanted to color the states such that none of the states will have. Is there a fill button here? Good. So for example, if we color California red, we can't put red into either Oregon, Nevada, or Arizona. Okay. So let's say you've got 4 colors to do that. What approach would you take to make sure that none of the states will end up with the same color? This is like a puzzle, yeah. Computer science is very much puzzle solving, right? It's if you like getting books of puzzles and riddles and things like that. In fact, that's how they recruited people for Bletchley Park. Bletchley Park was the famous code breaking unit during World War II that they used to break the Enigma code that the Nazis used. It was instrumental in the Allied victory. Separate them by time zones. Yeah, but then you might get two people on opposite sides of a time zone boundary with the same color. California doesn't exist. Like that. Go left to right? Okay. So what's your approach left to right? Torres. What approach would you take? Delete the states that make you do more work. Okay. You do every state individually. All right. So what color would you... Let's say our colors are red, red, yellow, green, and blue. And I apologize if anyone here is colorblind. Red, yellow, green, and blue. So which color would you give Hawaii? Top down, left to right? Okay. All right. Eliminate a color once it's used. Now you're gonna have to reuse colors because we only got 4 colors: red, yellow, green, and blue. Red, it doesn't matter. Yeah, I would say so. So if we wanted, we can color Hawaii red and Alaska red because they're not really connected to anything. Who cares? All right, so let's come to the. Sorry if you're from Hawaii or Alaska, but hey, you made it on the map at least. That's cool. Even though Alaska here is about the size of Arizona. Right, which is very inaccurate. Okay, so oh look, Hawaii is way over here. Yes, it made the map. That's cool. It's like the maps without New Zealand on it, right? What was the question again? So you need to, Mary, color a map. If you've ever seen like kids maps, you have to color a map such that no two states can have the same color, right? If I were to do that, then you wouldn't be able to see the border between Nevada and Arizona, right? So if you look at maps of the U.S., like that, you'll see that no two states have the same color next to them, right? So this one is 4-colored. Look at this. So that would be an answer. One answer would be find somebody that's done it already and copy it. Utah is touched by 5 states. You can't do it. Actually, there's more than 5 colors in this one. Or was the one I was just looking at? This one? No, that's 5-colored. Even though Utah is touched by multiple states, these guys, there's 3 reds touching it. Do you see that? But none of the 2 reds are touching each other. So it is doable. You can 4-color the map. Use one color in every other state as much as possible, then repeat that with the other colors. You can get penalized with plagiarism. Computer science plagiarism is an inherent part of the major. Now, on a homework assignment, yeah, you don't want to plagiarize. In real life, there are websites like Stack Overflow where people post solutions to common problems and people copy them all the time. So this should be an activity. Extra credit, because you can always just find one of these or done for you and color it. So, color state 1, check state 2 for colors nearby, color missing, repeat. All right, so let's start with, let's try that approach that involved every other state. All right, so we'll color every other state red. one's always painful. Okay. Alright, so we've now colored every other state, or more or less, you know, no neighboring states could be red. And then the approach was to do the same for yellow, so here, 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 here.
Don't read the whole paragraph. Don't read the whole paragraph. Just type in the answers we gave you. Don't read it. Don't read it. Don't read it. Don't read it. Just type in the answers to the question. Don't read it. Don't read it.
Rhode Island,
Yes, it is.
New Hampshire, and Maine. All right. And we'll do the same for green.
No spaces, all capitalized.
Green, 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 green. And then finally blue. Uh-oh. Got two blues. So we're stuck. So unfortunately, that approach does not work. Came very close to working, right? We got almost all of that. Michigan and Ohio also. Delaware. Let's get Delaware. Yeah. So Florida. So we unfortunately have two maps, two states on the map that we could not color properly. So if we're in a two-party system, the map would be more colorful, right? Vote the Green Party so that the map is more interesting. So the color of the Green Party is green. The color of the Libertarian Party is yellow. So that actually is the colors of the four biggest political parties in America. Isn't Montana touching South Dakota as well? It is, yeah. Good point. Okay, Michigan could be yellow. Oh, yeah, that's a good point, too. There we go. Unfortunately, Utah is stuck. We are stuck on Utah. So I'll let you guys think about that one. I'll let you chew that over in your head. Do you guys want to do that as a homework assignment? Try to, because you can always just look at the answer, right? So I need to come up with a new map that wasn't colored. That could be a fun homework assignment. Okay. I'll just need to find a map that isn't colored already. Would you provide the map? Yeah. I'll find a map and let you guys color that. See, all those years spent coloring in preschool, it's gonna come in handy in college. Give Utah a different pattern that's not solid. Yeah. Yeah, sure. I'll figure something out. And then just open it up in Paint and use the fill tool and just fill it in with colors and see if you figured it. Okay. Okay, so that's called map coloring, and that's actually a really important algorithm, believe it or not. Map coloring is actually really important. Which it doesn't seem like it should be. It doesn't seem like it should be. But what if I told you that like 3D video games need it? What? How? What? Yeah. So let's say that you've got a map. Let's see, can I do shapes? This shapes might work. Yeah. So let's say we've got some sort of map. It's top down, 2D, it doesn't really matter. Okay. And I wanted to convert this into triangles, because when you have a 3D game, it's basically drawing triangles on the screen really quickly. I don't know if you guys have ever seen this before. Do you guys know what I'm talking about? Color Australia. Going for the low hanging fruit, huh? Can I type? In South Australia, I was born. Heave away, haul away. Yeah, that's gonna be pretty easy. I think you probably two color this almost. No, you need three colors. Yeah, there you go. One color, Britain. That's funny. So, yeah, if you ever look at video games, they're made of triangles. Let's see. There you go. So everything you see in a video game is actually made up of triangles. Like this. Those are quads, but those are quads also. Triangles. Lots and lots of triangles. Okay. It's a point cloud. So by using enough triangles, you can kind of approximate any shape in 3D. So if you had a smooth surface like this, or if you have a polygon, triangulation, which I misspelled. So if you have any polygon, it's really important to be able to split it into triangles, because that's what you need in order to, if you had a smooth cylinder, then you need to break it down into triangles. You guys understand? So given any 3D object, you need to split it into triangles, because that's what your video card works with. And that it doesn't matter if you got a PlayStation or a PC or nothing, I guess. Why triangles? Because any surface can be approximated with a triangle, right? And so let's say you've got some weird polygon here. You can triangularize this. You can go like that, 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 and so any arbitrary 2D shape or 3D shape can be split into polygons, or any polygon can be split into triangles. And so your graphics cards are they're capable of processing lots and lots of triangles every second. And so that's what 3D game engines are optimized for. It's for drawing lots and lots of triangles on the screen, because you can approximate it. Like you got your coffee cup here. Looks like a smooth surface. If you use enough triangles, it will look smooth, even though it's not. It's still technically not smooth. So, how do you go about triangulating a polygon? Well, one of the ways you do it is by 3 coloring the vertices. So, having who came up with the ideas for a triangle? Probably a caveman. So you can come in here and do a 3 coloring of the polygon. And so what you do is you 3 color a polygon, and then those you just make triangles out of the 3 colors. Yeah. See that? So you can triangulate a polygon by 3 coloring. So pretty cool. Pretty cool stuff. You see that? So every triangle has 1 green, 1 blue, 1 red. Pretty cool. And yeah, so something as simple as that map coloring algorithm is used to take, you're in Blender or Maya or 3ds Max or whatever, which is these 3D modeling programs, and you have some sort of katana or something like that, and then it'll triangulate it into triangles for you. So pretty cool stuff. All right, so we've talked today about finding the minimum or maximum element. We've talked today about map coloring. What happened if the two colors touched? The world would come to an end. Created disruption of the space-time continuum. When you map color something like this, you can't have two touching colors, right? That's the rule. But the good news is you can always three color a polygon. Let's say it went out of order. Whatever. Let's make it red. You can always three color a polygon. It's pretty easy once you know the answer on how to do that. So that would create a triangle this way, this way. It doesn't necessarily give you the best triangulation, but yeah. And this is also used for what's called the art gallery problem, which imagine this is an art gallery now. So you're looking at the I don't remember if you said this, but are they always triangles? Yeah. In a video game, you can also use quads, and there's some systems use voxels, which are like, if you've ever played Minecraft, it's like having these blocks of stuff, you know, kind of, more or less. So you can make surfaces using quads as well, where you approximate these things using squares over and over again, but triangles are kind of your go-to system. So the art gallery problem says, imagine you've got art hanging on each of these walls. Okay, so you're looking top down again. This is a, this is Le Kearney Art Gallery. Spelled in French, Art Gallery. Okay, so imagine you got art hanging on all of these walls, right? It's like the Louvre or something. You know? So you got art hanging on all these walls, and you want to place cameras in the art gallery such that you can see all of the art, right? Because late at night, you want to make sure that somebody doesn't come in and steal the Mona Lisa again. All right? Did you guys know the Mona Lisa was stolen? Not recently. It's a while ago. Did you guys hear about that? It's actually the reason why the Mona Lisa is famous. The Mona Lisa was not famous until it was stolen. And then after it was found and returned, interest in it, skyrocketed. How do you steal a giant painting like that? The Mona Lisa is not really that big. It's stealable. I mean, not like I would, but oh my gosh, what the hell, dude? In the Mona Lisa gallery, in the gallery where it's being hung, it's just surrounded. Yeah, this is a typical shot of the Mona Lisa. This is not typical. There's usually 9 million people here, so and so the person literally just walked up, took it off the wall, stuck it under his shirt, and or rolled it up, stuck it under his arm, and walked out. It was not the Thomas Crown affair, It wasn't a person bungee jumping from the ceiling, and no, he just walked up and took it out. That was back when there weren't good security in art museums. Anyway, so let's say that you're running an art museum and you want to have cameras that can see all of the art on the walls, but you don't want to. You want to minimize the number of cameras, right? So if I were to put a camera hanging from the ceiling, let's say right here, this camera would be able to see that art, and 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 this one, but it can't see this one because it's around the corner. It can't see that one because it's around the corner. So maybe I could get away with just 2 cameras, like maybe 1 camera here and maybe 1 camera here. What do you guys think? Okay. Yeah, so 2 cameras. Do you guys understand? I don't think you can do it with 1 camera because these 2 guys are kind of on opposite sides. I don't think you can do any better than 2 cameras here. So Nicolas Cage stealing the Declaration of Independence. Yeah. Why still the Mona Lisa when there's so many other paintings? I don't know. Just liked it, I guess. It's a Da Vinci. You know, Da Vinci didn't actually paint that many paintings, so that might be why. I've seen one in the Hermitage in the Winter Palace in St. Petersburg. The 360 cam in the middle won't work, yeah, because it won't be able to see this guy. There's a wall in the way. Yeah, these 2 guys are the problems, right? There's kind of no way of they're kind of around the corner from each other. Okay, so this problem here, which again seems like, you know, why does it matter? Well, you know, this also has to do with 3D graphics and stuff like that. So if you do 1 there and 1 there, then you can turn this into, you know, maybe something like that. I don't know. But it's also used for triangulation and things like that as well. So these, there's a lot of these puzzles that just seem like, you know, like, yeah, they're just kind of funny, amusing puzzles. As it turns out, they're like the fundamental basis for like 3D graphics, you know, and stuff like that. So the one thing I did want to get to today though was sorting. So let's talk about that. So let's talk about the better ways of sorting. So if you remember last time, we talked about the bad ways of sorting. The bad way of sorting is you've got 10, 7, 20, -3, and if you're going to sort them from least to greatest, you need to make it. That's really hard to read, huh? You need to make it -3, 7, 10, 20. Okay. So how to go about doing that? The naive algorithm we had last time was we go through here, we find the smallest element, cut it out of here, put it in here, and repeat. So if you have n elements in the array, like 1,000,000, 1,000,000,000, whatever the size of the array is, that's n. Then n times you have to do n work, because to find the smallest element involves going over the entire array. And so 7 comes to here, 10 is the smallest element, comes to here, and then 20 is remaining, so it comes to here. Okay. So that would be what we call a n squared algorithm. So this approach we call order n squared. So the amount of work we do is proportional to the square of the size of the algorithm, and square of the size of the input. And so if we have 1,000,000 elements, we do 1,000,000 squared work, so 1,000,000,000,000 work. Whereas a better algorithm could do it in order n log n time, which is 20,000,000 operations instead of 1,000,000,000. So substantially faster, 50,000 times faster. Okay. So what is one of those better algorithms? Okay, let's talk about it. And this is going to be useful for you even if you're not a computer science major, even if you're just like a chemistry major, a physics major, or something like that, or any art. It doesn't actually matter. This approach is very, very useful. And this approach is called divide and conquer. Divide and conquer. Divide and conquer is an approach towards problem solving that we do a lot in computer science that is also just useful for real life. In fact, the term divide and conquer is like a military term, right? So if you have to fight 2 people, and they're both smaller than you, but together they're bigger than you. Like let's say you've got 3,000,000 troops, and country A has 2,000,000 and country B has 2,000,000. You can't fight them both at the same time. You'll lose. So what you do is you divide and conquer, right? So you get them to fight each other. You get them to not help each other. You take out country A. Then after you've recovered your strength, you take out country B. So that's an approach called divide and conquer. And this approach is in computer science means try to split the problem down into as small a problem, the great military strategy of kiting. Make sure you use frost magic. 1v1, man. 1v1 me. Okay. So, divide and conquer. So how could we divide and conquer this array? Well, we could split it into two halves, right? And then we can sort this pretty easily, right? So which one is bigger, 7 or 10? Tar traps, hunters, yeah. 7's smaller, right? So we just switch them if it's smaller, right? So 7 and 10. And then which one's smaller, -3 or 20? Okay, -3 is. So we switch these two as well. Now we're not done yet, right? So it's more sorted than it was before, right? But we're still not sorted. Now, as it turns out, if you have two sorted arrays, you can merge them together pretty easily. Okay, so if you have two arrays that are sorted, 1, 3, 5, 7, and 2, 4, 6, 8. How would you merge these together? What numbers would you get after you combine these two arrays together in sorted order? So we've got one sorted array here. Do you see how they're all sorted smallest to greatest? We've got another sorted array here called B. It's also sorted from smallest to greatest. What would the result be after you merge them? One, 2, 3, 4, 5, 6, 7, 8, right? And so this is the key insight as to what makes the thing faster. If you have two sorted arrays, you don't have to look at the whole thing. If you want to find out what the first element of the sorted array should be, all you have to do is look at the first number. You guys see that? So the first number is 1. And so we put a 1 here. Then we compare 2 and 3. Who's the smallest? 2. Okay. So we put a 2 over here. And now we compare 3 and 4. Who's the smallest? 3. Put 3 over here. You understand? So you only ever have to look at the first person in the array. And so the algorithm overall is actually very simple. If you have an array that you want to sort, what you do is you split it into just pairs like this, and then you merge. You swap the pairs so that they're in order, and then you merge the pairs together into groups of 4. And so in this case, we would look at the first element of this one and the first element of this one. Which one is smaller? Which one is smaller? Okay. -3. Okay. All right. Which one is smaller, 7 or 20? 7. We only need to look at the first one, right? We don't have to look at all the numbers. We only have to look at the first one. Which one's smaller, 10 or 20? 10. And then 20 is the last one, and so it's 20. So you guys see that? And so it merged these two arrays together to get the sorted array. Okay. And so this approach here is actually provably the fastest sorting algorithm at least in theory. Okay. And so it doesn't even seem that complicated, right? Like you just split it down into pairs, and then if the pair is out of order, you just switch them so that they're in order, and then you just merge the pairs together, and you're done. And if it's bigger than this, if you had like 8 numbers, you got 8 numbers. Then you split this thing into pairs and merge. So put 7 and 1 in order, everyone. So if you had to put 7 and 1 in order, what would you put it as? One and 7. What about 10 and 6? What about 2 and 3? 20 and -2. Okay. And so now we merge these two guys together into a group of 4. And remember, we can do that by just looking at the first element of each one. So what is smaller, 1 and 6? Between 1 and 6, which one's smaller? 1, right? Then after that, between 6 and 7, 6 is smaller. Between 7 and 10, 7 is smaller, and then 10 is the last one. And then over here, we're going to merge these two guys together. Between -2 and 2, -2 is the smallest, then 2, then 3, then 20. Now we're going to merge these two together. Okay. So again, we just have to look at the first element of each one. That's what makes this fast. We don't have to look at the whole thing. So when you're doing that selection sort every time you're pulling a number out, you have to look through the entire array and pull it out, and look through the entire array and pull it out. In this case, you only have to look at the first number. That's what makes it faster. So what is faster, 1 or negative? What is smaller, 1 or -2? -2. One or 2. Is that bubble sort? This is not bubble sort. Bubble sort is another garbage algorithm. Bubble sort, you keep constantly sweep over the array and switch things that are out of order. So you have to go over the entire array, which takes n time. You have to do that n times, because if there's an item at the very bottom, every time it would move up once every loop. And so bubble sort would be one of the 1 trillion operation things. There's 1. Okay. 2 versus 6, which one's smaller? Two. Three versus 6, who's smaller? This one is called merge sort. It's called merge sort. It uses the divide and conquer mindset. So what you do is you solve a small problem and use the solution to these small problems to solve the big problem. Okay. And so, yeah. So divide and conquer is the philosophy of this. So you split a big problem into small problems, you solve it for the small problems, and you use the solutions from the small problems to solve it for the bigger problems. And so this algorithm is called merge sort. You're gonna try and divide and conquer in real life, yeah. Take out your enemies one at a time, Jaden. That's the secret to success. Don't try and take on everyone. So did you merge by comparing indices of each array starting from 0? Yeah. Mm-hmm. Yeah. You start off by comparing the first element of each array, and whichever one you move over, then you just say, all right, I'm now looking at element 1 instead of element 0. You compare them. And so you just have a number that keeps track of where you are in each array, and you do a merged, sometimes called a zipper merge. Because you're merging two sorted arrays together into a sorted array, and you can do that actually very easily. And so this is actually the fastest possible sorting algorithm. So there's lots of sorting algorithms. This one's the fastest. Then there's other ones that are similar to it, similar running time. There's quick sort, which is similar but different. And there's heap sort. And all of these fastest ones are order in log in time. I think merge sort's probably the easiest to understand though. And so if you have a million, if your input is 1,000,000 elements, then it will sort it in 20 million operations, give or take. Whereas if you did bubble sort or selection sort, it would be order n squared. So merge sort would do it in 20 million steps, whereas bubble sort would sort it in 1 trillion steps. 20 million is much, much faster than 1 trillion. And this is the kind of thing that computer scientists care about. We care about speed. We care about efficiency. We care about speed. To a certain extent, we care about not wasting RAM. Not so much these days. Back in the day, RAM was $1,000 per kilobyte of RAM. Kilobyte, not megabyte, not gigabyte, kilobyte. And these are in like 1970s dollars, right? And so $1,000 of 1970s money is like, I don't know, like, how much is that today? A lot. So back in the day, we cared a little bit more about wasting RAM. Nowadays, just buy more RAM. Download more RAM. So, 1970, $1 in 1970 is $7 today. Yeah, so $1,000 would buy you 1 kilobyte of RAM. So that's $7,000 today for 1K, not 1 meg, not 1 gig, a K of RAM. So we used to have slightly different priorities, right? We would accept a little bit longer running time to save RAM. Nowadays, RAM's cheap. Nobody really cares too much. So. Okay. Computer programs can do this process almost instantaneously. If you had 1,000,000 numbers, yeah, you probably wouldn't notice it. Mm-hmm. My computer runs 3 billion, 4 billion times a second, so 20 million shouldn't be that bad. Are you allowed to post links here? Sure, go for it. Yeah, there's different visualizations of sorting algorithms and things like that. We're done. We're done with the class today, but yeah, that's a good one. There's also dancing. If you want to see how merge sort works through the power of dance. Insort, sort, bubble sort, quick sort. Let's come on. Where's merge sort? Merge sort. There we go. So you can watch these videos on how these things work using the power of dance. Will you have a weekly reading next week? Probably. Split into 2. Split into 2. Divide and conquer. Split into 2. The two of them compare each other. 2 is smaller than 4. Voila. Split into 2. 8's by itself, so it's sorted. Compares 0 and 6. This is what's happening inside of your computer. Yes, it's a bunch of people doing folk dances. That is correct. Okay, so that's it for today, guys. You can visualize those things if you'd like. They're kind of amusing, but again, you're not going to be expected to code this or anything like that. It's just a conceptual thing that you kind of have to understand. Okay, so that is it for today, and make sure that you do your a good chunk of the class didn't write the essay at all for the social issues, which is kind of disconcerting. It's only a page, so I don't know. I am available after this class. Yeah. All right. So let's say goodbye for now, and then yeah, Marco, just I'll hang out afterwards. Okay. All right. See you guys.